Today we're going to talk about transforming functions and different properties of quadratics. So before we do that, we're going to fill in these tables of values. So when I'm filling in a table of values, the x values are here, and I'm going to substitute them in for x to find out what the y or f of x is. So if I plug in -2 times -2 is a +4. -1 times -1 is 1, 0 times 0 is 0, 1 times 1 is 1, and 2 times 2 is 4. Then looking at the second one, we have the absolute value of x. And we know the absolute value is talking about the distance from 0. So how far away is -2 from 0? It's 2 units. Right? The absolute value of -1 is 1. Absolute value of 0 is 0. 1 is 1, and 2 is 2. These are called parent functions, which we're going to talk about. All right, this is the first day of sections 1.1 and 2.1 combined. First day of unit 2, section 1. A family of functions is made up of functions with certain characteristics. The parent function is the simplest form. So we just saw the simplest form of a quadratic and the simplest form of an absolute value. These are the parent functions. Functions in the same family are transformations of their parent function. So here we have 3 different parent functions: a linear function, f of x equals just plain x, absolute value, right? Absolute value bars of x, and a quadratic x squared, right? Linear is a line. Absolute value is going to look like a V that comes to a point, which is going to be called the vertex. And a quadratic looks like a U that comes to a point, which we're going to call the vertex. The domain of all of them would be all real numbers. Doesn't matter what the function is, we could put any value of x in. For a linear, the range is going to be all real numbers because it's going to go up forever and down forever, no matter what. For absolute value, notice both arrows are pointing up, and the lowest it went was 0, so that's y is greater than or equal to 0. And the same with the quadratic. The lowest it went was 0, so it's y is greater than or equal to 0. So ways we can describe transformations, right? Anytime we change size, shape, position, or orientation, it is a transformation. Horizontal translations, shift left and right. So it's always going to happen to the x value, and it's always the opposite sign. So if it's x plus k, that means it's really moving k units to the left. And if it's x minus k, it really means it's moving k units to the right. A vertical translation goes up and down, and it's going to happen to the y value. So it's going to happen after it. A reflection is going to flip the graph, all right, over a line of reflection. So a reflection over the x-axis applies to the y value, negative f of x. Also, a reflection then to the y-axis would apply to the x value, and that would look like f of negative x. All right, so that's over the y-axis. A vertical stretch makes the graph more narrow, so it's going to get closer to the y-axis, and a vertical shrink makes the graph get wider, right? It gets further from the y-axis. So it applies to the y value, and we're going to multiply k times the y value. It's a stretch if k is greater than, oops, this should say 1, and a shrink if it's between 0 and 1. So stretch greater than 1, shrink between 0 and 1. So let's look at this. The original function is here in red, the f of x, and we want to write a function comparing it to f of x. So really what happened is my vertex point started at 0, 0, and it went up 1, 2, 3. So that means we're adding 3, not to the x value, but to the y value. Up 3 looks like that. All right, another one. Now this is a quadratic. So we started with a vertex here, and we went over 1, 2 to the right, which is really like -2. So this is going to be f of, and it's happening to the x, x minus 2. All right, so you can try this one. You could pause the video so you can try it, and then check your answer. All right, so this graph moved down 4 units, so it's f of x and then -4. Another way to view these as being a vertex form for both a quadratic and an absolute value, looking at the transformations happening within it. So for quadratic, we have x minus h parentheses square with an a in front plus k. For absolute value, same thing, except instead of the squared, we have absolute value bars. For both of those, the vertex is h comma k. So opposite sign of inside, same sign as outside. So the H talks about how we're moving left and right, and like we said, it's going to opposite sign. Up and down is going to be the last number, the plus K. And then our stretch and shrink is in front, the A value. And if it's negative, that means it got flipped over the x-axis. It's a reflection. All right, so for each of these, we're going to identify the function family, describe the transformation, and identify the vertex. So this has a squared, so this is a quadratic. We can see that it moved +4 inside, which is really 4 to the left. And the +1 outside means up 1, which means that my vertex is going to be opposite, -4, comma, +1. All right, for the second one, I see these bars. There's no squared, so this is absolute value. We have a 2 in front, so it's a vertical stretch of 2, and also -3 means right 3, and -4 means down 4. And my vertex would then be +3, -4. The A value is not going to affect that. All right, my last one has the squared, so this is another quadratic. The negative is a reflection over the x-axis. 1/2 is a vertical shrink of 1/2. Then the +1 is really left 1, and the +3 is up 3. So my vertex is -1, +3. In order to graph a transformation, we're going to make the table of values for the parent function. So identify the function family and make the table of values for that parent function. We're going to change the x's and y's based on what transformations occurred. So we're going to do the opposite of whatever was with the x to the x values. So if it was x plus 5 in parentheses, we would do x minus 5. We're going to do the exact number after the function to the y values. So if it was y equals the absolute value of x, and then +2, I would do +2 to the y's. And then whatever was in front of the absolute value bars or the parentheses, either the negative or the A value, we're going to multiply that by y as well. And once I have my new points, I'm going to graph them. All right, so here we have squared. This is a quadratic, which means for my parent function, I'm going to have 4, 1, 0, 1, 4. We got those from the do now that we did. So the transformations that are occurring, the +4 in here really means left 4, and the -1 really means down 1, which means our vertex should be -4, 1. We're going to check that at the end after we've graphed it. So here we have x plus 4, so we're going to do the opposite, x minus 4. And afterwards we had -1, so we're going to do y minus 1. There was no number in front, so there's no number in front of the y. So every number in this column that was x, I'm going to -4 from it. And every number that was here in the y column, I'm going to subtract 1 from it. So if I were to graph these,
it's a ton of potatoes.
All right, so now I've plotted all these points, which means I can connect them into a U shape because it's a quadratic. And if I look here, my vertex, -4, oops, down 1, should have been -1, I missed that before. -4, -1, and that is correct, so that's a good thing I checked that. The domain, remember we said domain is always going to be all round numbers, so you could write the words all round numbers, I can write ARN, or the symbol for the set of all real numbers, which is like an R with an extra line. And my range, it was all above that lowest point there, which was -1, so y is greater than or equal to -1. We're going to learn another way to write this in the next lesson, but for now we're just going to write it as an inequality. All right, so you go and try this one. All right, it's another quadratic. So make your table of values, talk about the transformations, transform it, graph it, and answer the questions. Pause it, and then you can check your answer. All right, so this was left 5 up 1, which gave us a vertex of negative 5, 1, domain of all real numbers, and a range bigger than that positive 1. All right, it was x plus 5 inside, so we did x minus 5, and x plus 1 after, so we did plus 1. All right, and this next one, it's an absolute value function. So my parent function, when I do negative 2, negative 1, 0, 1, 2, are the absolute value numbers. So just all positives. My transformations this time, the 2 outside was a vertical stretch of 2. Plus 2 inside was left 2. And plus 3 outside was up right. So that means inside with the x was plus 2, so we're going to do x minus 2. I need 2 in front, so 2y, and then plus 3. Subtract 2's from this column. For these, we're going to start by multiplying them by 2 and then adding 3. So 2 times 2 is 4, plus 3 is 7. 2 times 1 is 2, plus 3 is 5. 2 times 0 is 0, plus 3 is 3. Then I get 5 and 7. So we'll graph these. All right, so that's my graph. My vertex, negative 2, positive 3. It's also always the middle one. So negative 2, 3. Domain we said is always all round numbers. And my range, my lowest point was a positive 3 here. So y is greater than or equal to 3. All right, this one has a few things. It's a quadratic, so we know we're going to have the negative 2, negative 1, 0, 1, 2, and square them. But I'm actually going to do something a little different. I have a 1/2 in front. So to take care of that, I might actually start to put some even numbers here. I might do negative 4, negative 2, 0, 2, 4 instead, just so I have less fractions in the end. So negative 4 squared is 16, negative 2 squared is 4, 0, 4, 16. Okay, so for my transformations, the negative in front was a reflection. The number in front is a fraction less than 1, so that's a vertical shrink of 1/2. Minus 2 inside really means I go right 2, and then minus 4 is down 4. So inside with the x was minus 2, so here we'll do x plus 2. I have a negative 1/2 in front, so it's negative 1/2 y, and then the minus 4. So we'll add 2 to all the x's. We'll multiply by negative 1/2 and then subtract 4. So that's negative 1/2 of 16 is negative 8. Negative 8 minus 4 is negative 12. That's negative 2 minus 4 is negative 6. 0 minus 4 is negative 4. Then we're going to have it symmetrical, so negative 6, negative 12. So it looks like we still can't fit those on here, and that's okay. We could probably go right off the graph, and it'll look okay. So we're going to have negative 2, negative 12, 0, negative 6, 2, negative 4, 4, negative 6, and 6, negative 12. All right, it's okay to go a little off the graph. I'm not going to give you anything crazy past it. So my vertex, middle number, board, looking at it, 2, negative 4. Domain was all real numbers, and the range, now it's the highest point. So I'm going to say everything below that negative 4. So y, that's not a y, is less than or equal to -4. So that's different than when it faced up. Right now it's less than, it's below it. So you're going to go ahead and try this last one. It's an absolute value problem. Pause, and then you could check your answers. All right, go ahead, check your answer. We have reflection in the x-axis because of the negative, a vertical stretch of 2 because of the 2, right 1 because of the x minus 1, and up 5 because of the plus 5. That means I was adding 1 to the x's and negative 2y plus 5 for the y's. My vertex was 1, 5. Domain was all their numbers, and the range was y is less than or equal to 5 because 5 was the highest point. That is it for transformations of functions.